Hello and once again welcome. After a break, we had finished extensively. Rudra, good evening.
Good evening, sir.
Are you able to hear me?
Yes, sir.
Are you able to hear me?
Yes, sir.
Okay, I am able to hear you. I thought that I should at least spend some time discussing with you the chemistry of transition metals. Just once I discuss that thing, will be more, you know, impressive on your mind. That's the reason why I thought of sitting with you. And if you are with me, then why not we make a public video so that others can benefit out of the discussion on the chemistry of transition metals. Let's start. As you know, that transition metals are nothing but the D block elements. They are the D block elements. But the actual definition of transition metal is little interesting. The new definition is not meant for guys like you, students of CBSE like you, or school students like you. The old definition is meant for you. The new definition says a transition metal is one which has an atom in a neutral state or in any stable ion, has incomplete d orbital configuration, incomplete, at least d1 to d9, not complete or vacant. So this was not there. This was added. Earlier, the definition was any ion, stable ion having incomplete d orbital. That category, scandium was rejected to be a true transition metal. Scandium for you is not considered as a transition metal. But now the new definition includes transition. Includes scandium as the transition metal. Because scandium forms only +3 state. None other than +3 does not show variable valency. Now the research has revealed that scandium can show 0 state, +2 state in some very complicated complexes, not simple compounds, complexes. So that is not in the purview of students, school students. So for you, scandium is not a true transition metal like zinc, cadmium, mercury. Zinc, cadmium, mercury does not use, they do not use any d electrons. So d10. Yes, mercury has +1, +2, us and ic, but they do not use any d orbital. Mercury does not use any d orbital in any of its stable ion. So these three in the new definition, scandium according to old definition, and for you, they are not true transition metals. Copper and silver, though, have D10 configuration, but they have stable, maybe less stable. Silver 2+ is less stable, but copper 2+ is highly stable in aqueous solution. And D9 configuration, which is incomplete. Gold has 3+, so they are transition metals. Copper, silver, gold, but not zinc, cadmium, mercury. And they show properties which are transition between S block and P block. Interestingly, they in the metal, there is metallic bond as well as covalent bond between atoms, sharing of overlapping of orbitals. That, along with the free electrons and the metallic, the positive codes, they attract. So both metallic and covalent. And why transition metals are so very important? Because they show colored compounds in their solutions, in their solid compounds also they are colored. They show variable oxidation state, good catalysts. They are hard, strong, dense, and high melting point, boiling point, high malleability, ductility, high thermal and electrical conductivity, high tensile strength, very similar physical properties. They have similarity along the series, also similarity along the group. They form complex ions easily. We have seen, we have extensively discussed the chemistry of coordination compounds. And the alloy forming tendency is wonderful. They are fairly unreactive, but they react under strong conditions. Now, many of them are paramagnetic, having unpaired one or more unpaired electrons. Some of them are ferromagnetic, like iron, cobalt, nickel, and this is a this is the magnetic oxide, ferrosulfuric oxide. As I have already told you, horizontal relationship as well as vertical relationship similarities there. They mostly form FCC, HCP, or BCC lattices, which unfortunately have not been now included in chemistry course. Group 11, copper, silver, gold, and group 8 to 10. This is the iron group. Then cobalt group is 9 and 10 is the nickel group, are more malleable. Electron configuration is very, very common to you, is known to you from time immemorial when you were studying periodic classification. Now there are anomalies, chromium and copper in 3D series. Now they are called 3D block elements. So this block, new term, I don't relish. 3D series. Now they said 3D block. The block is the entire block. And 3D block. Okay, let's be acquainted with the new term 3D block or 3D series elements from scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc, and chromium and copper. They have their anomalous electronic configuration of having half-filled and full-filled d orbitals. But the 4D block, yttrium, zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, silver, cadmium, they have many anomalies. Niobium, one electron shift from 5s to 4D, as well as molybdenum. I have not done it. Molybdenum, not technetium. Ruthenium, one electron shift. Rhodium, one electron shift. Palladium is two electron shift. It is diamagnetic. Silver, as usual, one electron shift, D10 configuration. And in the 5D block, 5D series, there are only two anomalies. Platinum, one electron shift from 6s to 5D, and gold is D10 configuration as like copper and silver. Oxidation state we have already discussed. Please bear with me. I'll be having cold here, and in Berhampur, Anil sir, must be colder than Katak. Now, the oxidation state I have taken a representation from the 3D series. Same thing happens with 4D and 5D. Scandium, yttrium, lanthanum, scandium shows only +3 state. Titanium, more and more electrons participate from the N-1D along with Ns. First, the Ns electrons go, remember, you already know the first Ns electrons go to give +2. And then one by one, the N-1D electrons go. So that maximum oxidation state for titanium group is +4. Now, why scandium doesn't show +2 state? Because The third ionization energy is relatively very less. And moreover, scandium 3 plus has a very high hydration enthalpy. So the driving force is to make it a stable, aquated ion or hydrated ion. That's why the moment the second electron jumps out, the third electron jumps out and hydrated. So there is no evidence of a scandium 2 plus formation, 3 plus. Yes, now the research has revealed in some interesting complexes, it does show plus 2 state and 0 state. But it's not in simple compounds of calcium, scandium, I'm sorry. So the oxidation state goes on increasing. Maximum oxidation state in vanadium is plus 5, chromium is plus 6, and manganese is maximum plus 7. And chromium can go so also plus 1 because chromium has molybdenum. They have 4s1 and 5s1, so they can show plus 1. And then the highest oxidation state goes on decreasing as the pairing begins from iron. The highest oxidation state goes on decreasing. Finally, the zinc group doesn't show any higher oxidation state than plus 2. Never. But yes, copper group can go up to plus 3. But common oxidation states have been, reddened, have been made red. But the actual reason for this is the high effective nuclear charge. Pairing with, sometimes we say to answer in board examination, because pairing starts from iron, then there is increasing resistance to participate electrons after seventh electron. The eighth electron up for NS2 goes, then after 5 electrons from n-1d, then the sixth electron doesn't. But the actual reason that the ENC, the effective nuclear charge, becomes so high that the sixth electron from iron is not interested to go out. But yes, as you know, the highest oxidation state in the entire block, D block, is shown by group 8, not by iron, but by ruthenium and osmium, which have tetroxide. Osmium tetroxide is very, very stable. I have already said all about this. Iron maximum goes up to plus 6, but its eldest brothers, ruthenium and osmium, then they can go up to plus 8, and that is the max, the entire D block. Hello and welcome those who are watching from the YouTube. Now and later, later means now, you will find the discussion is going to be very, very interesting, and that will be helpful for your examination. I will make this lecture examination centric than more examination centric, less knowledge centric. Of course, there will be knowledge centric in all my lectures. It will be my experience that takes the charge. The highest oxidation state is achieved by forming compounds or ions with oxygen and fluorine. Oxygen is more, fluorine is less, because oxygen can form double bond. Its valence is 2. And moreover, it can also act as a bridging element so that it can go so higher oxidation state. Manganese, dimanganese heptoxide exists because one oxygen acts as a bridge bridging atom between two manganese atoms. But MnF7 doesn't exist. So many fluorine atoms cannot remain. Although fluorine has a smaller size, but fluorine doesn't form a double bond to stabilize. Uh, you know, so many fluorine atoms surrounding manganese doesn't exist. This is very interesting. Rudra, this is very interesting. This is opposite to the inert pair effect, which we observe in the p block. It is the opposite. As you go down any transition metal group, scandium, then yttrium, then lanthanum, or any, say, titanium, then zirconium, hafnium, in any group, say copper, silver, gold, cobalt, rhodium, iridium, iron, ruthenium, osmium, palladium, platinum, sorry, nickel, palladium, platinum. In any group, you find the highest oxidation state in the group, as we have already seen the triangle. It looks like a triangle goes up and up and up to +7 and then goes down and down and down. Till the zinc group, it becomes only one valency +2. So as you go down any group, the highest oxidation state becomes more and more stable. In P block, it was more and more unstable because of inert pair effect. That the explanation was different. Here the explanation is completely different. Here it becomes easily possible to remove 4D and 5D electrons than 3D. Once the heavier metals attain their higher oxidation state easily by removing from their higher energy 4D and 5D, they don't like to gain electron. Once the heavier metals attain the highest oxidation state, they are stabilized by high hydration energy, hence have least tendency to gain electron and to be reduced again. So they are very stable. So iron trioxide, this iron 6 oxide or the corresponding ferret ion, this is 6, iron 6 ferret ion is unstable because iron in the +6 state. As you go down the group, ruthenium, even +6 is stable. +8 is little unstable. But osmium +8 is also stable. As you ruthenium can go up to +8, but it is little bit unstable. But osmium tetroxide is very, very stable. So as you go down the group, the highest oxidation state, iron doesn't have a +8, so unstable. Doesn't have. Even the +6 state is unstable. So the +6 state is stable here. And here, not only plus, I can write down osmium trioxide is really stable. Osmium tetroxide is also very, very stable. So this is the opposite. Remember, you get questions from this. Permanganate is very unstable. I mean, you prepare permanganate and you leave it and go to your village. You will find after you come back from village, it is decomposed. It is disproportionated into manganate, manganese dioxide, and oxygen has gone up. So self-disproportionation happens. So you have to prepare immediately and finish it. Say the +7 is the maximum oxidation state, but technetium is radioactive, as you know, the only element in the D block which is spontaneously radioactive and naturally. It is very, very, almost it is rare and extinct. And nowadays it is prepared for medical diagnosis and treatment purpose. Technetium 99 is prepared, synthetically prepared. So it's technetium which is radioactive. All others are stable, but many of them have radioactive isotopes, but naturally occurring isotopes are stable. So permanganate is unstable, but perrhenate is very stable and inactive. Inactive. Chromate, dichromate, they are unstable and good OAs. Molybdate and tungstate are stable and inactive. And the stability is maximum for tungstate. As you go down the group, it is increasingly easier to remove the 5f and 4f electron. sorry, 5D and 4D electron. Once they go and hydration occurs, they do not like to gain electron. And this is another thing. The cations of second and third row transition metal in a lower oxidation state, plus 2 or plus 3, are much more easily oxidized than the corresponding fast row transition metals. So since their higher states are stable, so the lower states are relatively unstable. So the lower states immediately lose electron and go to higher state. Once they go to higher state, they don't come back. I think you understand, Rudra.
Yes, sir.
It is, so very unstable. The lower states of molybdenum 3 plus and tungsten 3 plus are so unstable that they burst into flames in contact with air. Can you imagine? The lower states are unstable. They want to go to plus 6 tungstate, molybdate. So they are called pyrophoric. They burst into flames on contact with air. And plus 2 and plus 3 compounds with more electronic, already I have told you that you already know that plus 2 and plus 3 compounds, they are having more ionic character, less covalent character. If your oxidation state increases according to Fajan's rule, more polarizing power of the cation makes more covalent nature. That is known to you. And interestingly, the oxides and hydroxides are basic if the oxidation state is lower, and is the highest, then it is acidic. Chromium 6 oxide is acidic. It is anhydride of chromic acid. Chromium 2 oxide is distinctly basic, but chromium 3 oxide is amphoteric. So is the case with manganese 2 oxide is basic. Manganese 7 oxide is acidic, the anhydride of permanganic acid. Manganese 3 oxide is amphoteric, means it reacts both with acid and base. Interestingly, the plus 2 oxides, if you take only plus 2 oxides, uh, the basic character decreases. As the size decreases due to lanthanide contraction, not only the atomic size decreases, but also the ionic size, particularly taking the same oxidation state, decreases. Of course, some anomalies are there, but decreases. So there will be greater and greater polarizing power due to smaller size, and covalent nature will be more. And hence, the metal oxygen bond doesn't break easily. So the basic character decreases as you move in a series from left to right, keeping the oxidation state fixed. For example, plus 2 oxides. Example, titanium 2 oxide, vanadium 2 oxide, it goes on, the basicity, the base strength goes on decreasing as the bond between Fe and O or OH become more and more covalent due to decrease in size. Plus 1 state also is found for chromium, copper, silver, gold, mercury. 0 state also is found in many transition metals with their carbonyl complexes, with pi acceptor and sigma donor ligands. Pi acceptor and sigma donor ligands like carbon monoxide, 0 oxidation state is achieved by many metals like nickel, chromium. We have discussed extensively the chemistry of metal carbonyls in our coordination chemistry program. In general, the plus 2 state relative to plus 3 state stability increases from left to right in a series due to increase in IE3 as pairing increases, rather more correctly, as the effective nuclear charge goes on increasing, it becomes difficult to lose the third electron. So plus 2 state stability increases. And intermediate states, they show good tendency for disproportionation. Manganese 6 goes to manganese 4 and 7. So this is the clear-cut example where manganate ion, if you keep it, add a little bit of acid, then it will immediately disproportionate to permanganate, manganese dioxide and water. I am talking of permanganate decomposing is a different way. Permanganate giving potassium manganate, manganese dioxide and oxygen gas. It is decomposition, it's not disproportionation. There permanganate +7 to +6 +7 to +4, two reductions and one oxidation where oxygen from -2 to 0. That is not a disproportionation, but this is disproportionation. Manganate with the help of acid will disproportionate to permanganate and manganese 4 oxide. Similarly, cuprous will be slowly disproportionating to metallic copper and copper 2 plus. Now, this is very important. You have to remember that these are the exceptional examples where the +2 state is unstable. Otherwise, +2 state in aqueous solution is highly stable, more stable than copper +1. Although this is a D10 configuration, this is a D9 configuration. The reason is that copper 2 plus has a smaller size, more hydration energy. So the unfavorable or the second ionization enthalpy is far more compensated by greater enthalpy of hydration or hydration energy that compensates for the second ionization energy. So high hydration enthalpy for copper 2 plus uh, far more compensates for the IE2 of copper. So that is the reason why copper +1 being D10 configuration is less stable in aqueous solution than copper 2 plus having D9 configuration. The key is hydration energy. And these are the two examples where copper 2 iodide and copper 2 cyanide, they are unstable. The moment they are formed, they undergo disproportionation. This it goes copper 1 cyanide, the copper 2 cyanide or cupric cyanide gives cuprous cyanide and cyanogen gas. This is cupric iodide gives cuprous iodide and iodine molecule. So this is a precipitate, this is a precipitate. Is white, all are white precipitates. These are unstable aqueous solution, unstable. They undergo disproportionation. You cannot say disproportionation, you say auto redox, where iodine from -1 to 0 and copper from +2 to +1. Similarly, the carbon here is from +2, cyanide it is +2, and in cyanogen it is plus carbon is in +2 and this is in +3 because cyanogen, as we have done cyanogen, the structure is this. So there is homolytic cleavage and carbon loses 3 electron, so it is +3 here, but here cyanide is +2. So this is the oxidation and reduction is from +2 to +1. So these are not really disproportionations, they are auto-redox reactions, self-redox reactions. Now see the interesting, as we continue, more and more interesting discussions will take place. Why oxidizing strength is in the order vanadilyl ion, these are oxocation, this is oxide anion, oxoanions, these are oxocation, vanadilyl ion, dichromate ion, then permanganate ion. Just by simple electronic configuration, you can explain without invoking any electrochemistry, without invoking the standard reduction potential. You can say that chromium goes from +6 to +3. In +3, it is D3. So all the 3 electrons, they are singly occupied in T2G set. So that is half filled T2Z, that is stable. And manganese goes from +7 to +2. This is +7 and it goes to +2 in acidic medium. So this is +2 is Mn +2 is D5. Half filled stability, in fact, It is, manganese 2 plus, as you know, is a very weak field metal ion. In the metal spectrochemical series, it is in the first place. So it's the weakest metal to split the octahedral field. So all are singly occupied, the T2Z as well as EZ. So it's all symmetrical and stable. We say it is upfield stability. And vanadium 3 plus, it goes from plus 5 to plus. This is in plus 5. Now goes to plus 3. D2, no extra stability. T2Z2, so it is not symmetrical. So no symmetry energy, no extra stability. That is why, in a very classical sense, we can answer that vanadil is the weakest OA, then dichromate, then permanganate. Why oxygen is more efficient in elevating a transition metal to its highest oxidation state than fluorine? Because oxygen can form a double bond. Oxygen is a good oxidizing agent. So also fluorine, no doubt. And now this is not between fluorine and oxygen. Together. Why fluorine and oxygen? Because they are good oxidizing agents. The lattice enthalpy, if it is ionic compound, if it is covalent, the bond energy, they are high because of the small size of oxide and fluoride ions or oxygen and fluorine atoms. So this is the reason why the small size fluorine and highly electronegative, highly oxidizing fluorine and oxygen, they are used to elevate a transition metal to its highest oxidation state, not seen in chlorine or bromine or any other oxidizing agents than fluorine and oxygen. Between fluorine and oxygen, oxygen number one. Although the chlorine, the reduction potential is 2.87, there is more than this. Fluorine is a more oxidizing in nature than oxygen. Even then, oxygen has the power of having divalency. It can bridge. Fluorine cannot bridge two metals. It has got advantage. It can form p-pi, d-pi bonding to stabilize the bond. So which fluorine cannot. This is nickel plus 4, platinum plus 4. Nickel, the third and fourth IE are very high. Platinum, palladium less. So they can go up to plus 4 state easily. Nickel cannot go up to plus 4 state easily. Why the lower oxides like Cr2 oxides is basic, Cr3 oxides is amphoteric, and Cr6 oxide is acidic? Why? Because in a lower oxidation state, there are more d electrons which it can donate. And the one which can donate electrons, they are Lewis bases. So we have to apply the Lewis concept to explain why Mn2O manganese oxide is basic, because it has got 5 electrons in the d level, Mn plus 2 state. Well, as the number of electrons will be very, very less in Mn plus 7, there is nothing, no electron in D and S. So it will only accept. That is why the highest oxidation state oxides are acidic. The lowest ones are basic. And the intermediate ones, they have intermediate number of electrons and some vacancies. They can accept, they can also donate. Why oxo anions are formed by highest oxidation state of the metal? Because oxygen is highly electronegative and small size and a strong OA. Hence, the oxo anions, when it is there formed, they go to the highest oxidation state of the metal. And about atomic size, you guys know, but since it is going to be a very planned lecture today, I will be talking something about atomic size for the benefit of those who are now watching or will be watching later to benefit. Now, I have given extensive data which you can benefit later, but I can explain these three curves. This is the 3D series, this is the 4D, this is the 5D. So start from scandium, then it goes on slowly decreasing. You find the decrease is so very drastic. It's not a drastic. If you look to the data, you find a small decrease, and sometimes remaining constant. And towards the end, copper and zinc, it increases again. But there is a net decrease, and that is the D block contraction. So there is a convincing increase in size as you go from the first to the next element down the group because of the addition of a new cell. But the third element is nearly same as I used to say, excepting lanthanum, yttrium, and scandium, yttrium, and lanthanum. There is no lanthanide contraction effect found in lanthanum. But later on, from hafnium onwards, you find the atomic sizes are very, very similar. Sometimes you can say bahu same, as I used to funnily say, bahu same, because of the lanthanide contraction effect. This you know. I have written down, I will share in the description box. You guys will find the file which you can benefit. The data table is also there in angstrom. In picometer, you can multiply by 100, 169 picometer, 144. In nanometer, it will be 10 times more, 16.9. So I have given in angstrom. So 4D series, 3D series, 5D series. And this is the real trend. And if you compare the ionic size, taking +2 as the standard for all the metal ions, there should be a decrease. And that is due to, say, D block contraction. But there is an anomaly. There is a decrease and then increases and goes up to, and in manganese, a little more. It sits in a hump. Then again decreases. And towards the end, that was not found in atomic size, in covalent radius, but in ionic size of +2, because you have recently studied the Jan Teller effect. Of course, that was in chromium and copper, but here it is manganese, doesn't matter. But similar type of situation is happening. Manganese 2 plus is not only has a bigger size than ferrous, which is expected, but also bigger size than chromium as well as vanadium. So that is the thing. Density, you guys know that they are highly heavy elements. Scandium is the lightest, about 3 gram per centimeter cube, and all rest is about 5 and above. The highest is here, osmium and iridium. They are more or less same. At 1 atmosphere, osmium has a higher density, slightly higher density than iridium. But high pressure, at 1 atmosphere, osmium is little heavier than iridium. But at high pressure, iridium is heavier than osmium. So I always rate them, they are more or less equally heavy. But the real situation is this. And in a series, it goes on increasing up to certain element, then decreases. In a group, it goes on increasing with no anomaly. But situation in melting point, boiling point, it is very interesting. Similar, it increases up to certain element in a series and then decreases. That's okay. But down the group, you find there is anomaly. It increases similar to density for group 3 to group 10 to nickel group. But group 11 and 12, it is little anomalous. Group 12, it goes on decreasing. Both melting and boiling point goes on decreasing. Zinc greater than cadmium, and mercury is a liquid having the least melting point and boiling point respectively. And the reason is that it is D10 full metallic bond becomes more and more weaker, and we can apply the relativistic contraction, the quantum mechanical effect, the relativistic contraction effect in mercury having 6s, which is being because of the contraction, high speed and contraction. They do not take part in metallic bonding. They are themselves heavy. So the density is 13.6, but the metallic bond is so weak that they become liquid at room temperature. So zinc group, the melting point decreases, so also the boiling point. Obviously, you know melting point is less than the boiling point. But in the copper group, group 11, the situation is little intriguing. You have to remember, melting point, silver, copper is the highest, silver is the lowest. But in boiling point, gold is the highest, silver is the lowest. That is same for melting point and boiling point. But there is a swapping between copper and gold in melting point and boiling point. Melting point, copper is the highest, and in boiling point, gold is the highest. And already, just like you saw how Mn2 plus has a higher size, but here in the melting point graph, you will find there is a dip. If you look to the melting point graph, this goes on increasing. It should have increased and then decreased, but the dip comes at manganese, that hump in size, but dip in melting point. So also in the 4D series, there is a dip. Technetium is less than ruthenium, of course, less than molybdenum. Manganese is less than iron, of course, less than chromium. So this is very interesting, but that is not found in 5D series. Rhenium is less than tungsten, is not less than rhenium. Rhenium is less than tungsten. I told you, those who are watching from the YouTube, or you who now is watching participating in Zoom, that for getting a good position in IIT main or NEET, you have to categorically, repeatedly, I tell you, you must study the NCERT book line by line. You should not miss any single sentence. If possible, unfortunately, I never ever encourage the art of cramming, memorizing. You have to do that. If at all, it is something which is not which demands you to memorize, like colors of different metal ions in the aqueous, the aqua complexes. What is their colors? It is coming. So you have to remember by studying multiple times or remembering in the way you know better than me. So you find two anomalies here in the 3D manganese, but there is no such anomaly. Goes to a maximum of to tungsten, then decreases. It goes to maximum chromium and molybdenum, and then suddenly shows a dip and then increases, then decreases. So I have given extensively melting point, boiling point data for 3D, 4D, and 5D. Then coming the interesting thing. Then it comes very interesting thing. We enter into electrochemistry. We enter into electrochemistry. Those who are little deficient in electrochemistry, don't feel discouraged. Try to listen to me what I'm saying. Excepting 10 metals, what are the 10 metals? These are the three triads in the group 8, 9, 10. The second triad, ruthenium, rhodium, palladium, and the third triad, osmium, iridium, platinum. Not iron, cobalt, nickel. They are good reducing agents. Their SRP values are strongly negative. Group 8 to 10, but not the first triad, second and third triad, and entire group 11, copper, silver, gold. Group 8 to 10 horizontally, two triads, and group 11 whole, copper, silver, gold, and one from group 12, mercury. They have positive SRP, means they cannot displace hydrogen from dilute acids. They are not good reducing agents. But others are very good reducing agents having negative SRP, standard redoxon potential. As you know, today, nowadays, when you say electrode potential, it means standard reduction potential, and I am very sad when IUPAC changed standard electrode potential to reduction potential from oxidation potential. Anyway, we have to agree and follow. Now, if we look to see the interesting data, how the standard electrode potential E naught have been calculated. You know, this is the guiding principle from electrochemistry. I'm writing down here somewhere del Z naught is equal to minus N. Sorry, I'm not making it complicated. This is NF N F Faraday E naught. So this is E naught is equal to minus del G naught by NF. NF, the number of electrons to which oxidation state it is going or coming from. F is Faraday constant, and this is, you know this. And if del G will become negative, then negative becomes positive. E naught will be positive. And if del G naught becomes positive, the E naught will be negative. Del G naught positive, I'm talking of now how I'm sad for the IUPAC making it SRP. I'm talking of this process. Metal solid going to M2 plus AG. That means oxidation tendency. That means we are talking of oxidation potential. Becomes, if it is delta Z negative, then E0 positive. And you will find in earlier literature, they're all positive and they were from M to M2 plus. But now it is M2 plus to M, which is not the case. Metals are good reducing agents. They really go from 0 to plus 2. But we are studying the opposite way. So now you consider these are all plus and we are talking of oxidation potential than reduction potential. It is easier to understand. Let us not dishonor what IUPAC has asked us to believe or to presume. Let us presume, but let us understand that these are all oxidation potentials. The relative tendency for a metal to be oxidized from 0 state to the plus 2 state. And these are the values. These are plus, 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 and copper is minus. The only copper is minus, and this is again plus. The only minus is copper, so far as SOP, oxidation potential, is concerned. And the signs will be opposite when you are talking of SRP, which I have given. But I will be discussing in terms of oxidation. But really they undergo oxidation as they are good reducing agents. But we know that negative values of SRP means the reduced state component is a good reducing agent. A positive value of SRP means the oxidized state component of that couple is a stronger oxidizing agent, we know. Now see the values I have given. The sum total of the 4 energy terms that will decide the enthalpy factor. Of course, whenever we fail to explain by only enthalpy factor, then we have to bring in entropy factor. It is actually del G, which is equal to del H minus T del S. So entropy factor will rescue us whenever the enthalpy factor will not be able to explain to us satisfactorily. Unless such complication happens, until it happens, we will explain only talking about the total energy involved when a metal from the solid state is vaporized first, needing the heat of atomization. Some people call it sublimation energy, and then first ionization enthalpy, second ionization enthalpy. These are all positive terms, and then it will be plunged into water undergo hydration, not hydro, I'm sorry, hydration, so that it will liberate hydrogen energy. So one term is negative and three terms are positive. Sum total is positive. All the four energy, they add up to a positive value. So the lower the positive value, greater is the tendency for oxidation, and hence greater is the SOP and lower is the SRP. So all these fit into what we have studied. So it goes on increasing. Some anomalies you find I have reddened. Manganese has a sum which is very similar to that of vanadium. Therefore, the E naught is 1.18 and 1.18 same. Suddenly there was a decreasing trend. When I'm saying decreasing trend, I'm not considering sign. I am taking positive sign and I am talking of SOP. So there is a decrease, there should be a decrease. But because of this particular manganese has a unusually low atomization energy that makes the total positive, despite having a lower value of the hydrogen enthalpy, the sum total is not increasing, rather it is nearly similar to that of vanadium. So its potential is same as that of vanadium. Now it goes on increasing and you find the highest is in the case of, and see, because of a very low sublimation energy or heat of atomization of zinc, the value, the positive value is nearly same as that of, chromium. It is lower than chromium. Here we have to bring in some entropy parameter so that it should be why it's lower energy means it would have been greater than 0.91, but it is really little less than 0.91. So some entropy factor has to be brought in to explain. These are experimental calculation of the single electrode potential by coupling with standard hydrogen electrode or calomel electrode, whatever, a glass electrode, whatever, reference electrode is experimental and you have to explain why. So whenever the enthalpy factor, it is actually the free energy factor, del G factor is the reality. But we don't tell to students the intricate calculation del S factor in sometimes, manganese 2 plus has all electrons unpaired. 5 electrons, all are unpaired electrons, and they inside the aqueous solution, they are strongly, they are oriented and induce water so that the entropy increase is not much because of the interaction with water molecules, their electron circulation, and the unpaired electrons, the increase in the change in entropy is not much like others. So some entropy factor has to be brought in, but unless otherwise needed, we will not complicate the explanation. But here, okay, similar we say is because of similarity in the values. Zinc has a positive SOP and negative SRP, and copper has the highest. So much so that the entropy factor also is not possible to make del Z, negative. So del Z is positive, so E0 is negative. When I say E0, I mean SOP. The immediately SRP concept is the opposite sign minus. Yeah, you are understanding, I hope, Mr. Rudra.
Yes, sir.
Yes. So I have highlighted for manganese, the factor is the same heat of atomization, and for zinc, it is same heat of atomization, and for copper, making so high, it is the second IE of copper. Because after losing the first electron, it has D10 configuration. To 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 break down the stable D10 configuration, you need much higher energy. So the high, see much higher 1960 is the second IE that makes the total energy positive. So much so that del Z naught is not remaining negative. It is becoming positive. So that E naught becomes negative. Which E naught? Yes, Rudra, which E naught I'm talking of?
Sir, SOP.
Yes, oxidation potential. We are all explaining, understanding through oxidation concept and then changing the sign to realize that more the negative SRP, stronger is the reducing strength of the metal which is in the reduced state component. Now, which I have already explained everything, reducing strength, titanium, then vanadium, which is equal to manganese, then chromium is 0.91, then zinc 0.76, then iron 0.44, cobalt is 0.28, nickel is 0.25, and copper is not at all a very good reducing agent. Yes, compared to others it can be better, but compared to this is poor. It cannot displace hydrogen from acids because its uh, SOP is negative, SRP is positive. This I have already explained to you. Now there is another interesting game that we will play. That is ferrospheric. I mean 2 plus and 3 plus. Again, we are bound by the IUPAC rule 3 plus 2 plus. Of course, this is better. 3 plus is an oxidant, 2 plus is a reductant. And we will see, you will find that manganese 3 plus 2 plus, cobalt 3 plus 2 plus, and iron 3 plus 2 plus. They have positive values. Forget about nickel, copper, and zinc, which are so unstable. 3 plus are so unstable. Therefore, because their reduction potential are so highly positive, 4.2, 4.67, their plus 3 states are never achieved. Even if somebody brings to the plus 3 state of nickel, copper, zinc, it immediately is demoted back to plus 2 state. So we don't consider nickel, copper, zinc for plus 3. But yes, manganese plus 3, cobalt plus 3, and ferric, iron plus 3, they are very good oxidants. Positive SRP means their oxidized state components are very good oxidants. And between them, which is strongest, it is 1.97, cobalt 3 plus, then Mn 3 plus, then Fe 3 plus. Then having negative values are titanium, vanadium, chromium. They are they are good reducing agents. They means who? You have to tell Rudra. They means who? Yes.
Sir, athletic question to
Titanium, vanadium, chromium, they have negative SRP. So they are good reducing agents. They means who?
Oh, sir, Mn 3 plus, metal 3 plus.
Are you kidding me? The couple contains two components. The reduced state component is the reducing agent. The oxidized state component is the oxidizing agent. So when you are talking of 3 plus and 2 plus, that couple, for manganese, iron and cobalt, they have positive SRP, means the oxidized state component, Mn3 plus, Fe3 plus, cobalt 3 plus. They are oxidants. And between them, cobalt 3 plus is highest, followed by Mn3 plus, followed by Fe3 plus. And these have negative SRP, means they are good reducing agents. But which are reducing agents?
Sir,
Yes.
Ti2 plus, B2 plus,
Their
Cl2 plus.
reduced state components are good reducing, are the reducing, not good, they are the reducing agents. So they are plus 2 states, this titanium 2 plus, vanadium 2 plus, chromium 2 plus are good reducing agents because their SRP, 3 plus 2 plus SRP are negative. And between them, if you grade which one is the strongest reducing agent, is chromium 2 plus. More is the negative, better is the reducing strength. Then chromium, then titanium, then vanadium. They are so good reducing agents that they displace hydrogen gas from dilute HCl. Do you believe it? Metals displace. That we knew that metals displace, except in copper in 3D series. And in the 4D series, it is rhodium, palladium, and silver, not even cadmium. And in the 5D series, you have ruthenium, rhodium, ruthenium, osmium, osmium, iridium, and platinum. And group 11 total, copper, silver, gold, and mercury from group 12. These have, positive SRP or negative SOP, so they cannot displace hydrogen from dilute acids. But now we find these are the 3 plus 2 metal ions having negative SRP. They are able to produce hydrogen gas from dilute acids and themselves go to their plus 3 states. You understood?
Yes, sir.
And when I scanned all the questions, I'll give you the site today, from where from you will do it very easily, that everything comes from this discussion that is given in the book, in the NEET as well as main examination. In a twisted manner, but from the book. Sometimes you hear why Mn 3 plus is a strong oxidant. You can explain because Mn 2 plus to which it will go has a D5 configuration. Why, while these have vanadium 3 plus to 2 plus is a negative SRP, so that vanadium 2 plus is a good reductant because of high hydrogen enthalpy of V3 plus. Therefore, the opposite reaction is favorable, positive. So we are unfortunately studying the reduction process, but we are doing the oxidation process. Therefore, V2 plus is a good reductant, can displace hydrogen from acids. You understood?
Yes, sir.
I have already explained. And reason for cobalt 3 plus becoming better oxidant than Mn3 plus because of the smaller size of cobalt 3 plus. The hydrogen energy comparatively is more for cobalt 3 plus, which makes the overall energy process favorable. Delta G is favorable, so much so that its E naught is becoming 1.97, where it is 1.57. Course, if you look to I3 value, it's not very supportive. They're more or less same, but only the size factor is responsible to, it will go from plus 3 to, no, plus 2. Both way it is, it will go from plus 3 to plus 2, and this will also go from plus 3 to plus 2. So here, if you compare between this, 74 is much less than 82. Because it's a real process happening, not the unreal process that we study here. This process is not happening. That is to understand the table, reduction potential, but really the opposite thing is happening. Um, if you are asked a question why Cr2 plus is a good RA and Mn3 plus is a strong OA, is a, we already know chromium 3 plus 2 plus has a negative SRP, and chromium manganese 3 plus 2 plus has a positive SRP. That you can write down electrochemical data. But in a layman's point of view, chromium goes from plus 2 to plus 3 as a reductant. It goes to plus 3 with D3 configuration, stabilized by the Hapfield T2G, this 3. You can argue why not chromium plus 1 the reverse way. Supposing chromium 3 plus, why not it is going to chromium plus 1 or going to plus 2? Because chromium plus 1 has a larger size than 2 plus. So it is, hydrogen energy is low. Therefore, chromium 3 plus will go to chromium 2 plus. Hence, chromium 2 plus will be the reductant and it will go to chromium 3 plus. Ionization energy, you know the trend that go from accepting scandium series, which goes on decreasing. In all others, the third element has the highest value because of lanthanide contraction effect, which is found after lanthanum, hafnium to mercury, and that effect percolates up to lead. The P block we are not discussing now. But the first to second element, there is a decrease and then sudden increase to the highest value. That is not the case with vanadium, chromium, and nickel group. It goes on increasing from start to finish. And in all other groups, it decreases and then suddenly increases to the highest value. And the highest value in each series is the last element, zinc, cadmium, and mercury. In all the entire D block, mercury has the highest ionization enthalpy. On one hand, mercury is a liquid having very poor metallic bond strength, high density, but having high ionization energy. But remember, measurement of density, measurement of size, these are all bulk phenomenon. You are measuring the size in a crystal lattice or in an aggregate. But ionization enthalpy is not an aggregate, it is a atomic phenomenon. You are vaporizing into atoms, individual atoms, then you are plucking out electron in the gaseous state. So the situation is different. Because of the relativistic contraction effect, mercury needs a much more energy to lose electrons, so it has highest ionization enthalpy. And of course, lanthanide contraction effect is there. But the so high energy is not only explained by lanthanide contraction. It is for all these, the relativistic contraction effect will also add to its reality. So all these are depicted in graphs. This is 3D series. It goes on it goes on increasing, and then there is a slight decrease, and towards the end, this is copper, this is zinc. So highest is zinc. In size, it was happening decreasing and then increasing, but it is increasing and increasing and increasing, and highest is zinc. And some anomaly is found in palladium, in this and here. So that is not to be remembered. But what to be remembered is that scandium group, there is a decrease. 3D, 4D, and 5D is not. Uh, where is the mercury group? It starts from where? Oh. It is not shown. It should be little lower than this here. So, but after lanthanum, hafnium onwards, it is the highest. This is hafnium. Oh, this is 3D. This is 4D. And there is a decrease in 4D. And in the case of the titanium group, titanium and hafnium, they have exactly the same IE. But I used to say the third element has the highest, but it is same as titanium. It decreases to zirconium and then becomes same as titanium. But in all other cases, you find the third element is the highest. Chromium and copper have high IE2, because after removing one electron from 4s1, the stable half-filled configuration has to be dislodged. So therefore, the second IE is a little more. So therefore, but zinc has a relatively lower IE2, because you are removing from 4s1, 4s2. The same s orbital is losing electron. But here you are losing electron from D. Second electron is to be lost from D, which is stable now, half filled now, or full filled now in copper. So they have relatively higher. So zinc has a lower IE2 than chromium and copper, IE2. IE3 of manganese and zinc, they are higher, because the plus 2 state attains half filled and full filled. Therefore, the third IE is greater. You have to look to the electronic configuration. Then to explain the third IE or fourth IE, the previous electronic configuration you have to look for. IE3 of nickel and copper are higher, because their plus 3 states are not attainable. due to high Z star effective nuclear charge. It's not due to electronic configuration, because this is 28, this is 29, so much of nuclear charge. The effective nuclear charge is so high. And we have already explained electrochemically that their SRP value is 4.1 something. In zinc, 3 plus 2 plus is 7. 4.6 is copper, 3 plus 2 plus, so 3 plus is really not attainable. In a layman point of view, you will say I3 are very high. Because nickel losing 2 electrons and then 1 electron, then third electron is not breaking down any half filled or full filled, but you have to look for the high effective nuclear charge. Is it going well, Mr. Rudra?
Yes, sir.
And how is the speed? Is it okay with you?
Yes, sir.
We will be finishing. Titanium and vanadium, although their SRP values are very encouraging, but in true sense, they are passive. They become passive with non-oxidizing acids like HCl, conc HCl. Therefore, after some time, the reactivity decreases because of the passivity. Although they have highly negative SRP, they should be more reducing in nature, but in reality, because of the passivity, slow down of reaction, it becomes passive. And this is important. Transition metal solutions, mostly they are colored. And the color is already, this might be due to DD transition, or for oxo anions or cations, it is CTS, charge transfer spectra. Sometimes in complexes like carbonyl complexes, nitrito complexes, so there is a pi bond, there can be both DD transition as well as CTS. And in CTS, it could be both metal to ligand or ligand to metal. And it's very, very strong peak. As you know, this is an allowed transition. And the DD transition, del L 0, is a forbidden transition, therefore it is weak. It is buried inside a strong CTS transition that you know. Mostly it is DD transition is the cause of color, but in oxo anions like permanganate, dichromate, vanadil ion, these are all due to CTS, ligand to metal charge transfer, LMCT. And some are colorless because D0, D10 configuration, or the entire absorption occurring in the UV region, and it's complementary also falling in the UV region, so nothing. Some tail, if it comes to the visible region, then it absorbs near violet, and then it looks yellow. So that also sometimes doesn't happen in some complexes where del naught is so large that the entire absorption spectrum falls in the UV region. And you have to remember this copper 2 aqua. All this aqua, if you change the ligand, then complex color will change. Aqua complexes, you have to remember, this is blue, copper 2, cobalt is pink, 2. Cobalt 3 is yellow brown. Manganese 2 is pale pink, 3 is violet. Iron 2 is green, iron 3 is orange. Let us make it orange. Orange. Wow, orange looks. This orange? I really.
Yes, sir.
Orange or yellow or brown. It varies depending on concentration. It can be yellow. It may be little dirty also, like brown. Brown କୋଉଟାକୁ ଆମେ କହିବା? Can you
Sir,
brown?
red tall.
Huh?
ତଳକୁ red ତଳକୁ
ଏଇଟାକୁ କହିପାରିବା କି?
sir ତା ତଳକୁ
ଏଇଟା ନୁହଁ?
yes sir ଠିକ
Oh, ଛାଡ଼ brown. Chromium 2 is blue, chromium 3 is violet. Nickel 2 is green, titanium 3 is purple, titanium 4 is colorless, A0, D0 configuration. Titanium 2 ଗୋଟେ କୋଉଠି ଥିଲା? Titanium 2 ଏଇଠି ଦେଇଦେଇଛି, titanium 439 2 ଦେଇନି 2 ର କଲର ଏଠି ବି ନାହିଁ ସେଠି ବି ନାହିଁ doesn't matter 2 is colored no doubt 4 is colorless D0 vanadium 2 is violet vanadium 3 is green vanadium 4 is blue and you have a table I have borrowed it from NCRT there is a little mistake I found and there is some other mistake I forgot to correct you can check this is correct and here cobalt 2 plus is pink cobalt 3 plus is yellow brown. This is D7, cobalt 3 plus is D6. Then catalytic property is fantastic. And you have two types of catalysis. I think I asked you to study catalysis after chemical kinetics. Have you studied that? Have I sent you the file for catalysis? Heterogeneous and homogeneous?
No, sir.
No or yes?
No, sir.
And enzymatic catalysis? Enzymatic catalysis, enzyme is a biocatalyst. You have to also study catalysis. That is a part of chemical kinetics. I will send you the file. You can understand everything. So in heterogeneous catalysis, the phenomenon occurring is adsorption. This, usually the catalyst is a solid and the reactants are adsorbed on the surface. Adsorption, colloidal state, adsorption is also a part of solid state. I think, have you studied adsorption phenomenon? Have we studied adsorption, chemisorption and physisorption? Or I have asked you to study of yourself?
Sir, we haven't studied.
Then adsorption also you have to study. You have to study adsorption. Colloidal state and adsorption you have to study. That was, we used to take up that when we take up solid state. Immediately after solid state, we take up colloidal state and then adsorption. So I will give you two files for you to self-study. One is, and ask your doubts. One is catalysis, the other one is adsorption. So in heterogeneous catalysts, the catalysts are usually solids. The reactants are adsorbed on the surface of catalyst. And because of the coordination of the metal, it may be a physical adsorption, van der Waals forces, or sometimes chemical forces. The activation energy gets lowered. And once the activation energy is lowered, it becomes faster. The catalyst is, doesn't do anything, doesn't change any equilibrium constant, doesn't change the position of equilibrium, but only hastens up, speeds up by lowering the activation energy. So because of adsorption, interaction between the solid catalyst and the reactant, there is a physical bonding or a chemical bonding, there is a reduction in, and the reaction takes place on the surface. A is adsorbed, B is adsorbed, they sit side by side like they are sitting side by side in a field and talking with each other, and then they react. Once the A and B reacts on the surface of the solid, then they are uprooted, they are dissolved. Adsorption, the opposite is desorption. They are dissolved and they go as AB. So during this process, the activation energy is lowered. There are many catalysts like titanium tetrachloride, Ziegler-Natta catalyst for polymerization, stereoregular polymerization. This is used along with organometallic compound, triethyl aluminum. Vanadium pentoxide, preparation of SO3, the P block. Manganese dioxide, decomposition of KClO3 to give KCl and oxygen. Iron nowadays used as a catalyst in manufacture of ammonia in Haber's process. Earlier it was iron oxide. Now it is used iron oxide. Previously it was iron. Now it is iron oxide. Nickel, palladium, platinum, they are used as as catalysts for a reduction of unsaturated organic compounds. Ferric chloride for aromatic chlorination as halogen carrier. Copper, dehydrogenation of alcohols, catalytic dehydrogenation. Platinum, preparation of NO from ammonia and oxygen. Palladium chloride, palladium 2 chloride is a catalyst for Walker's process to prepare aldehyde from alkenes. And innumerable number of transition metals and their compounds acting as wonderful catalysts, heterogeneous catalysts. Now there is homogeneous catalyst. In homogeneous catalysis, the catalyst and the reactants remain and products remain in one phase, either all gas or all aqueous solution or all solid state, usually or liquid state. Usually, I have taken from the book, from the NCERT book, this example, and it is asking in a NEET examination and in IIT main. This question is asked several times. For the oxidation of iodide ion to iodine by peroxydisulfate ion, it is catalyzed by ferric ion. Some ferric chloride is added. It enhances, speeds up the process. Otherwise, it becomes very, very slow. How? Because the catalyst, the step one, the catalyst ferric ion first oxidizes iodide to iodine, and itself reduced to ferrous. And this ferrous is really brings about reduction of peroxydisulfate to sulfate, where oxygen in the peroxy group, the internal peroxy linkage, the bridging peroxy linkage was -1, and here all -2. So reduction happens when peroxydisulfate ion changes to sulfate ion, and ferrous is very prompt to reduce this. But only iodide is not a good oxidant to good reductant to reduce peroxide to oxide, but ferrous is a good reductant. So ultimately, ferric ion is regenerated acting as a catalyst. So by that, the net activation energy is lowered down, favoring the process. Alloy formation is fantastic because they are similar size. Their sizes, like the main group elements, the sizes are much different. So there is a mismatch between their sizes, and due to heterogeneity, they do not crystallize to form a stable alloy. But because of similarity in sizes, the transition metals, they add up, they mix up homogeneously, and they form a very homogeneous alloy with a strong metallic bond. Complex formation is superb. And if you are asked a question why the transition metal ions, they are uh, heroes for forming complexes because of three reasons. They can go up to high charge, +2, +3, +4, and more. And that increases the polarizing power of the cation. Small size of the ions, this buy one, get one free. If the charge increases, the size decreases. Ions means metal ion. So the first 2 points increases the polarizing power of the metal ion, and most importantly, the availability of vacant d orbital of appropriate energy, 3D, 4D, depending on how we have discussed the stability. 3D is suitable for, this is hard acid, hard base, soft acid, soft base. So the vacant d orbitals are of appropriate energy to accept electrons from the donor ligands and form complexes. These are the three reasons. They can form non-stoichiometric compounds because they show variable oxidation state. They can have some crystal defect, metal deficiency defect, or metal excess defect, so that the stoichiometry, the simple stoichiometry 1:2, 2:3, that is lost because some ferrous ion, they are missing from their points, lattice points. And to equalize the charge, some other ferrous has been converted to ferric. Therefore, the iron to oxygen ratio is not becoming 1:1 as is found in normal stoichiometric ferrous oxide. It becomes little less than, this is called metal deficiency defect. That is a program in solid state which we unfortunately could not. So due to due to defect in the crystal of those compounds, transition metal compounds, oxides, carbides, nitrides. So you find the formula is non-stoichiometric. They form non-stoichiometric compounds because of variable valency. They also form interstitial compounds because they can hide small size atoms like hydrogen, carbon, nitrogen in their interstices or voids. Because not, I'm not saying defects, in their voids, because naturally FCC, BCC or CCP crystals, they have some voids, octahedral voids, tetrahedral voids, cubic voids. So they can hold small size atoms, and these are called interstitial compounds. They, though their malleability and ductility is less, but they are very harder and stronger and more heat resistant than their corresponding non interstitial compounds. I mean, virgin transition metals. Steel contains a lot of carbon embedded, hidden in the interstices. So it is an interstitial compound. Iron forms an interstitial compound with carbon, and the bond is metallic. So the carbon atoms, though they are non-metals, nitrogen or hydrogen, hydrides, carbides, nitrides here. I have given the example of hydride here, nitride here, carbide here. These buy one get one free interstitial compounds, they also are non-stoichiometric. How much of carbon you are introducing, how much of hydrogen you are introducing interstices, that depends on the ratio between iron and carbon, iron and nitrogen. So interstitial compounds are often non-stoichiometric, and due to crystal defect also it is non-stoichiometric. Formation of oxides. This is very important. As I have told you, scandium doesn't show, for you, scandium doesn't show any plus 2 oxide. Because plus 2 state is non-available for you. So for you, scandium is not a true transition metal, but according to new definition, yes, it is. Scandium has a 3D1. So the atom, neutral atom has 3D1, and now it has been found by research. This, you know, covalent nature increases with increase in OS. And manganese 7 oxide is a green oil, is covalent because of high oxidation number. So also vanadium pentoxide and chromium 6 oxide have low MP because more covalent character, lower is the melting point. And less oxidation state is more basic. The intermediate is amphoteric, which we already know. The higher oxidation states are acidic, we know. The reasons are also we know. Exception is vanadium, the highest oxidation state is +5. Vanadium pentoxide, it is often asked in the examination, is not acidic. It is also acidic, it is also basic, it is amphoteric. It is not only acidic, it is also basic, it is amphoteric. While it's lower, vanadium 3 oxide and 4 oxide, they are basic, but 5 oxide is amphoteric. Unlike in other cases, the highest oxide is acidic, vanadium pentoxide can react with base to form vanadate, same +5 metathesis, non-redox reaction. And also it reacts with acid to form the cation, oxocation, vanadilyl ion, same +5. These are oxocations. And V2O4 in the +4 state also is a basic oxide. It only reacts with acid to form vanadilyl ion. So these are all metathesis, non-redox reactions. Remember this with care. Now we are going to the last part. Potassium dichromate and potassium permanganate. This is my program for transition metal, general trends, and the chemistry of KMnO4 and potassium dichromate. But in another program, which I may not do, I'll ask you to study of your own, is metallurgy and the chemistry of iron, copper, particularly most importantly iron, copper, that is most important, and some other extraction. In extraction, you will find silver, gold, and other molybdenum, other processes will automatically tell you. So metallurgical processes and chemistry of some important transition metals and their compounds. Iron, ferrous sulfate, .7 water, the chemistry of that. Copper, copper sulfate, .5 water. So that you have to study. I am only taking off transition metals. general trends. And this potassium dichromate can be prepared from chromite ore. Chromite ore is FeCl2O3. It is just like FeO dot Cl2O3, just like Fe3O4. Analogous to, you can say, put an analogous sign. Having inverse spinel structure. Forget about inverse spinel. If you have studied in physics, it's okay. FeO dot Fe2O3. But instead of Fe2O3, you are adding Cl2O3 in chromite ore. So iron here is in the +2 state. This iron in chromite ore FeCl2O4, this iron is in the +2 state. It goes to +3 state here. Chromium is in the +3 state. It goes to +6 state. So when take the chromite ore in a sodium carbonate solution, in mild basic sodium carbonate solution, bubble oxygen gas, continuously on heating condition, you will get this redox reaction happening. Chromium +6 chromate ion, yellow solution will be formed along with a precipitate of ferric, reddish brown precipitate of ferric oxide, and carbon dioxide will go up. Then you take the solution. This is precipitated. The solution AC is treated with acid. So chromate, dichromate, there is always a conversion. Always you get a question like this. I'll tell you. When you add acid, chromate will be converted to dichromate. This yellow will be converted to orange. And when you add alkali, I have given it here, then again orange is turned into yellow. Then sodium dichromate is formed, but sodium dichromate is more soluble. Potassium dichromate is less soluble. Its solubility product is less for potassium dichromate. So you have to go for a double displacement reaction with KCl to get a sparingly soluble potassium dichromate. So when you add acid, it becomes orange. When you add alkali base to dichromate, orange will become yellow. So this interconversion happens. And a question in these years, 2025, you will be giving in 2026. 2025, you have got, you will find, you will get a question. I'll give you the site. You will do that. It chromate treated with acid. Then again, that A treated with base. Coming back to pavilion. So to continue with dichromate, dichromate has a SRP of 1.33. So dichromate ion is a good oxidant. I'm sorry, it is a good oxidant, but less than permanganate is 1.51. So the structure is this. There is an oxide link bridge with 126-degree angle, and this tetrahedra, two tetrahedra joined by oxide bridge, and chromate ion is tetrahedral. Of course, there will be two double bond O and two single bond. This is not correct. And here also two double bond, and so dichromate ion has the power to oxidize many reductants like H2S to sulfur, ferrous to ferric, iodide to iodine, stannous to stannic, hydrogen peroxide. This is very important. Immediately you will get chromium 6 pentoxide. This is not chromium 10, this is chromium 6 because there are two peroxy linkages. In CrO5, there is one normal oxide and two peroxides. So it looks like as if it is chromium 10. There is nothing called chromium 10 in the group 6. It has 4s1, 3d5. So it can go up to +6 state max. So it is +6. So it is a metathesis reaction in the beginning. So hydrogen peroxide just there is retaining the peroxy linkage in chromium 6 oxide, parapentoxide. Then if you leave it, if you just want to extract it in some ether solvent, you will get a blue violet substance solid CrO5. It's unstable, but you can have it. But if you leave it, it will decompose to form, then redox reaction happens, chromium +6 becomes +3 and oxygen gas is released. But this part we don't show. When you write, potassium dichromate plus sulfuric acid plus H2O2. We get oxygen plus chromium sulfate, chromium 3 sulfate plus potassium sulfate plus water. But the reality is this. It goes via chromium 6 pentoxide. It converts ferrous to ferric. Oh, I have repeated. I am sorry. And S2S to S, I have repeated this. And many other reductants to the higher oxidation number. Uses leather industry and for preparation of many azo compounds and so on. Can you balance this equation? Just to revise the ion electron method in acidic medium, dichromate oxidizing ferrous to ferric. You have to be very thorough in oxidation. I mean, this ionic equation and balancing by Owen method or by ion electron method. If it is ionic, you can go for ion electron method or Owen method. So what is this? Cr2O7, 2 minus giving you Cr3 plus. Plus you have to multiply by 2. 7 oxygen, so 7 water. Then 14 hydrogen, then 14 H plus. Then 6 electron. So there is balance, charge balance and atomic balance. All balance is done. Then ferrous is converted to ferric. So there is no oxygen, nothing. So there will be only loss of 1 electron. So, oh sorry, multiply by 6 and tell me what are the coefficients. And you add this multiplying by 6 so that 6 electron get cancelled and you get Cr2O7 plus 14H plus 6 Fe2 plus gives you 6 Fe3 plus 2 Cr3 plus 7 water. Okay.
Yes, sir.
Now KMnO4 is the last. You can prepare KMnO4 by from pyrolusite ore, which is a very common ore of manganese, MnO2, pyrolusite. You digest with KOH, fuse with KOH, fuse the pyrolusite ore after crossing grinding with KOH in presence of any oxidizing agent, including oxygen. You can take KOH also, KNO3 also, sorry, KNO3 also as an oxidant. So oxygen you can bubble so that Mn from +4 state, it will go to +6 state for manganate. I'm sorry, potassium manganate. This is manganese 4 oxide will be oxidized to potassium manganate. Potassium manganate is a green color, dark green color substance which is paramagnetic. Permanganate ion is diamagnetic, is tetrahedral. But manganate ion is MnO4 2 minus, has 1 unpaired electron, is paramagnetic, green, and that is purple. Permanganate is purple, and MnO2 is black. So then the second step, you take manganate, add some water, acid. So on acidification, the manganate ion disproportionates to +7 and +4. You get back MnO2, no doubt, you can recycle, but you can get, this is a precipitate, MnO2 is a dark, it's a black precipitate, and permanganate ion comes in the solution, which you can take it and then crystallize to form KMnO4. You can use in place of oxygen here as oxidant, you can take KNO3 also in place of O2. Nowadays, in manufacturing process, once you get the first step is over, the manganate is converted to permanganate by electrolysis in alkaline solution. Instead of chemical process, electrolysis helps in the loss of one more electron from manganese +6 to +7 and converts very easily at the anode where oxidation happens by loss of electron. The other method, laboratory method, is to convert manganese salt. Somebody is plodding with the heart emojis. Who is that? Can anyone tell me? Is it you, Mr. Rudra?
No, no, sir.
Or it is the YouTube itself is plodding? The YouTube, with the help of maybe AI, is watching us doing something very serious. Is flooding with the heart emojis. Is flooding now. It is stopped. Is there anybody who is watching? Yes, some are watching directly. Maybe he or she watching directly is flooding with heart. Thank you, if it is so. Now, here you can also take, instead of taking, yeah, one of the methods in laboratory is taking peroxide disulfide salt, which can oxidize the pink, the very light pink color to purple color permanganate, in itself being reduced from peroxy to oxide -2. It is the -1 here and -2 here. Manganese from +2 to +7. This is a laboratory method. Instead of peroxide disulfide, you can use lead 4 oxide, hypochlorite ion, you can also use. Then it is a dark purple or black solid. In solid state, the purple color is not observed, it looks black. It is isostructural with perchlorate ion. Permanganate ion is tetrahedral. And it has got not very high solubility. It is soluble, but less soluble. 6.4 gram in 100 gram water at 20 degrees Celsius or 293 Kelvin. And it decomposes on heating to manganate, manganese dioxide, and oxygen. It is paramagnetic. Oh, oh. Immediately, I am talking of here. Manganate ion is green and paramagnetic. Permanganate ion is diamagnetic. And the isostructural with perchlorate ion is already written. And there is a d pi p pi bonding between manganese with oxygen. Oxygen P and manganese D. There is a pi bonding, d pi p pi, back bonding. No, bonding, not back bonding, bonding. So I've shown you the permanganate ion here having no unpaired electron, and one is missing. One unpaired electron is there in manganate ion. Manganese, manganese having 7 electrons, 2 plus 2, 4, 5, 6. Where is the other electron? Here. This is 5s2, sorry, 4s2, 3d, 5. Total 7 electrons are participating in bonding. So one unpaired electron is there. It's paramagnetic. Now, permanganate is a versatile, more versatile reducing agent. In strongly basic solution, its SRP is plus 0.56, not much, but it gives only manganate. But in neutral medium or weakly basic medium, it goes to MnO2, black MnO2 plus 4 state. Of course, one of the products is OH minus. Even if you do not take OH minus, take neutral solution, but the product is OH minus. Its SRP is very close. But if the medium changes, strongly basic means you get manganate. Weakly basic or neutral means you will get manganese dioxide. But it's acidic, its SRP is much higher. In acidic medium, it goes to +2 state. If it is very acidic, is less acidic, then it goes to +4 state. But this is the most common one that you will be using in your examination. This, where 1.51 volt is the SRP for permanganate and 2 Mn2 plus. Is a stronger OA than dichromate, because dichromate was 1.33 and this permanganate is 1.51 in acidic medium, and therefore nobody uses chloride ion. HCl you don't take as acid. In dichromate you can take HCl, nothing will happen. It will be simply producing acidic medium, because dichromate doesn't have the power at standard condition to oxidize chloride to chlorine, because it's 1.33 and chlorine chloride is 1.36, is very close. But if you change the conditions from standard to non-standard, anything can happen. Delta G can be negative. But usually we don't take chloride to chlorine. That oxidation is not taken with dichromate ion, but easily chloride ion can be oxidized to chlorine gas with permanganate. Therefore, for acidifying, sulfuric acid is used, not hydrochloric acid. You can have another independent reaction, KMnO4 plus HCl giving you KCl plus MnCl2 plus chlorine plus water. Now, like potassium dichromate, in acidic medium, permanganate can oxidize oxalate to carbon dioxide. Dichromate, thick, same. nitrite to nitrate, but this is more versatile than dichromate. Sulfite to sulfate, chloride to chlorine, ferrous to ferric, S2S to sulfur, and itself changes to 2 plus. Can you balance this in acidic medium? You can do it in the same manner as you did, no doubt. You can do it. A neutral or faintly alkaline medium, as you found that MnO2 is the product. So here, iodide will not give you iodine. In acidic medium, had it been iodide, yes. But in neutral or mildly alkaline condition, it goes to plus 5 state. Iodide high jumps to plus 5. Iodate, where iodine has a plus 5. This is very important. You have to remember. In neutral or slightly alkaline medium, iodide is not oxidized to iodine, to iodate ion, and itself, as in, in the neutral medium, I have already told you it is reduced to MnO2. So you get black MnO2. Same is the case, thiosulfate ion, which was not a reductant in this condition, it gives sulfate ion, not sulfur. The extra sulfur also is not being detached. Sulfate ion and itself get reduced to MnO2, and OH minus is automatically formed. But only difference is that if you take Mn2 plus along with permanganate, then Mn2 plus is oxidized to Mn4 plus and MnO4 minus is reduced to Mn4 plus. So the common product, this is a comproportionation reaction. Comproportionation reaction where the common product is plus 4, and here you generate acid. You are not taking acidic, but progressively you are generating acid. You are starting with alkaline, slightly alkaline or neutral medium, particularly neutral medium, but you are generating acid. So we are coming to the end. KMNO4 used in laboratory titration where no other indicators are used. It is a self indicator. The last drop will change the color from colorless to pink or purple. That will show the endpoint. It is not a primary standard because it is unstable. Plus 7 state for the first row L3D series is unstable. As you go down the group, the stability increases. So KMNO4 is prepared in situ every time when you go for titration as an oxidant, redox titration, as a bleaching agent for wool, silk, textile, due to its oxidizing property, and itself get reduced. So the color goes, it bleaches that, it bleaches the color of the wool and silk, but itself also is decolorized. It's a good OA in all reactions, uses multiple reactions. So this is the reference where recently research, not recently, from 90s also they have found scandium can show 0 and plus 2 state, for which the IUPAC was forced to change the definition of ransom metals, but for you it is still. Now, I was just looking to see how easily you can answer this. This is the site from where you can get IIT JEE questions. I was looking to, of course, lanthanides and actinides are also there, which I will take another class. Before this year ends, we will have to complete lanthanides and actinides. And don't hesitate to tell me if you want any class, my presence with you, even if it is first week of January, I will sit with you because we are all competition minded. Buy one, get one free. If you study well, then of course focus in English and literature and all that during the last month, then nobody can, prevent us to secure more than 85%. But what we need is a good position in IIT, or if not by bad chance, then a good position in NIT. And now see this problem. The number of ions from the following that have the ability to liberate hydrogen from dilute acid is dash. Tell me. The multiple choice is there, but I it is there. 1, 2 or 3 or 0.
सर V2 plus.
Huh?
V2 plus.
How many number? It is a numeric question.
V2 plus सर सब तक हो सर तीनटा.
What is the answer?
सर 3.
3. Yes, 3. I mean, देखिथिले केवल the only titanium, chromium, and vanadium 3 plus 2 plus SRP was negative. So their 2 plus were good reductants. They are so much good reductants that even the metal ions in their plus 2 state are able to displace hydrogen from dilute acids. So check answer. You can check answer. It is correct. You understood?
Yes sir.
So you will find some questions are from lanthanides and actinides, but most of them are transfer metals, which you have done. And from electronic configuration and finding their spin only formula, their dipole moment. Magnetic dipole moment, you can do n into n plus 2 square root bm. Okay? So
Yes
these
sir.
are, and first ns electrons goes and then n minus 1 d electron goes, that you know. That is very cool. Now see, this one, 7. The amphoteric oxide among this, upon reaction with alkali, leads to formation of an oxide ion. The oxidation state of vanadium in oxidation oxide ion is what? That means out of the three, you have to select which is an amphoteric. If you
सर
select V2O4
V2O5.
intermediate like others, then you are gone. V2O3 and V2O4 are basic, but V2O5 is amphoteric. That is the only exception we found. Yes or no?
Yes sir.
So V2O5 plus 5 means plus 5. Whether it is vanadate ion with alkali or vanadil ion with acid, it will be plus 5. It will be metathesis, non-redox reaction. So the answer is plus 5. The answer.
V2O5.
No. What is the answer? Plus 4, plus 5, or plus 3, or plus 7?
Plus 5. Plus 5.
Correct. Now see how much necessary is to know the color. Right. See, question number 2. The first transition series metal, the M, has a highest enthalpy of atomization in its series. Can you remember? I have given you the 4 data: heat of atomization, that is sublimation energy, first IE, second IE, and the hydration enthalpy. So in the first column, have you marked out of all these scandium to zinc, which has got the highest heat of atomization?
Sir vanadium.
Yes. That means you have rightly remembered. You can have a look now. Then how much, analytically you have to study the book and understand things. Now see, vanadium is 515. Lowest is zinc. And the second highest is this one, titanium. Minimum is 130 and in between is manganese. So, first you have to catch which is the metal. Metal is vanadium. And when it is aquated, solvated to give a Mn plus, exists in green color, then you have to see vanadium, you have to look to the table. You have to remember that. Can you tell me which vanadium, 3 plus or 2 plus or 4 plus or 5 plus is colorless, but 2 plus, 3 plus, 4 plus they are colored. Which one is green? The nature of the oxide. Again the same question. If it is 5 plus oxide is green, then V2O5 is amphoteric. But it is saying nature of oxide of the metal is dash. I mean, let us see the options. You will find basic, neutral, amphoteric, acidic. Now you have to see vanadium. Which one is green color? 3 or 4 or 5? 5 is colorless. Which one is green?
Sir, sir 2 की 3 जोटा भी बस ताले दीटा का बेसिक हो.
If you look at the color list, vanadium 3 plus is green. We cannot say arbitrarily. Vanadium 2 plus aquated by hydrated ion. Vanadium 2 plus is violet. Vanadium 3 plus is green. Okay.
Yes, sir.
Therefore, this has to be 3 plus. 3 plus means V2O3. V2O3 and V2O4 they are basic. Only V2O5 is amphoteric. So the answer will be basic. Yes or no?
Yes, sir.
What you are saying?
सर मैंने B2O5 ଟା କଲରଲେସ୍ ହବ ଆଉ ବାକି ଯୋଉ ଦିଟାଙ୍କ ରହିଲା ସେ ତ ବେସିକ୍ ହବ ସେଥିପାଇଁ ସେମିତି
Theta, that is not the primary. Primary is color. You are forgetting.
Yes, sir.
Unless you know which oxidation state is green, you cannot say that it is what. So ago green देखिलो table रे मन पड़ला जे green two टा होची violet, three टा होची green. So three टा आसिला. Ago vanadium. First you caught vanadium has the highest heat of atomization, enthalpy of atomization. Then the oxidation state कोटा colored होची aqua complex टा होची green. That is 3 plus. Then you remember 3 plus and 4 plus they're basic, 5 plus is amphoteric. You understand?
Yes, sir.
So in this way, I have given you the entire, there are so many questions here. Out of them, maybe 20 to 30, maybe less, 20% will be lanthanides and actinides, which we will study. Now see, this one. All from the book. These are all 25, 24, 23, 22. 22. 2002 to 2025. So these are initially. Now see this question. Potassium dichromate, when you add alkali, it will become potassium chromate. Yes or no?
Yes, sir.
When you add acid, again it will become potassium dichromate. So this is potassium chromate. It is potassium dichromate. Of course, to balance, another potassium sulfate has to come. It is KOH achi. So you have to balance. Water jibo. But here another K2SO4 will come. So the choices are potassium chromate, dichromate ta chromate haba alkali re. Then acid dele pun dichromate hejibo. So 8 chromate and dichromate. Hela?
Yes, sir.
So in this way, you solve all Mn2O7 is a oil at room temperature, correct? B2O4 reacts with acidic acid to form, yes, it is correct. Because it, no. B2O4 is basic. It reacts with acid to form in BO2 2 plus, the vanadium oxidation number is how much?
+6.
हाँ तेणु एटा तो +4 अच्छे एटा wrong. Cr2 oxide is basic, correct. P2O5 does not react with acid. No, it is amphoteric. It reacts with acid to form vanadium ion and base, that is vanadate ion. So the correct ones are A and C. No?
Yes, sir.
So it's A and C eta. C eta. Yes. So once you thoroughly study, you will get all answers correct. ତା ଭିତରୁ କିଛି ଗୋଟେ ଦିଟା ଖଣ୍ଡେ କ୍ୱେଶ୍ଚିନ୍ ମେଟାଲର୍ଜିରୁ ଅଛି, ତାକୁ ଯଦି ପଢିଛ କରିଦେବ, ଯଦି ନ ପଢିଛ ମତେ ମେଟାଲର୍ଜି ମାଗିନ. ମେଟାଲର୍ଜି ମୁଁ ଦେଇଛି ଫାଇଲ. ହାଭ୍ ଆଇ ଗିଭେନ୍ ୟୁ ଦି ଫାଇଲ?
No, no, sir.
ମେଟାଲର୍ଜି ଫାଇଲଟା ଦେବି with along with some few transition metal chemistry like copper and zinc. copper and iron. And metallurgy ଭିତରେ zinc ରହିଯାଉଛି, zinc ର metallurgy ରହୁଛି, and gold and other metals ରହୁଛି. Gold, silver, molybdenum, titanium ଏଗୁଡ଼ାକ କେମିତି extraction ହୁଏ, କୋଉ method ରେ, ସେ ବି ରହୁଛି. So I'll give you. So with this we conclude today, and don't hesitate. ମୋର ଯେତେ କାମ ଥିଲେ ବି, ଯେତେ ଅସୁସ୍ଥ ଥିଲେ ବି, ମୁଁ ଟିକେ ହିରୋ ମାର୍କା ହେଇଯାଉଛି. With age I must settle down with limited physical activity. Sometimes I become so wild. ମୁଁ ଯେତେବେଳେ ବାହାରକୁ ଯାଉଛି ଏତେ wild ହେଇଯାଉଛି, ତାପରେ 2-3 ଦିନ ପଡ଼ିଯାଉଛି. So with this we conclude, and those who are watching, who have watched, who is watching, who are watching, and if you find this discussion interesting and helpful to you to get a motivation for the coming examination, or any further examination, then you don't hesitate to subscribe to my channel if you have not, and also put a thumb, hit on the like button to motivate me. Bye bye. And I will be shortly, announce the class, maybe 29th. Tomorrow and day after tomorrow I'm a little busy. 29th I will be, somebody is flooding with, yes, heart. Are you doing? Are you flooding with heart symbols, Rudra?
No, sir.
No, somebody else. Thank you, thank you. Who is flooding with heart symbols, emojis, and lanthanides and actinides will have one class. That will be a short class, and maybe in that class, if we can discuss important aspects of metallurgy and yeah, that, let me think of. And you don't hesitate to tell me if you need any class of any subject. Bye bye.
प्रणाम
ଆଉ କ'ଣ
सर।
କହୁଛ? ଆଉ କାହାର ଦରକାର?